Welcome back. This is the second of 4 videos about kinetics. So the last thing we covered in the first video was given the definition of rate as the change in the concentration of a species. For example, it could be the products, but we could also calculate the change in the concentration of the reactants over a certain time interval. So this is a definition of rate, but there are actually different types of rate that we could be interested in studying. So we have the instantaneous rate, and we covered that in the other video. The average rate we will cover in this presentation, as well as the relative rate and the rate laws. So we have, this is something we have already covered in the other presentation, but basically the instantaneous rate can be determined as the slope of the tangent to the curve that describes how the orientation, the concentration of the substance varies over time. So you can see here that we have on the y-axis we have the concentration as molarity. On the x-axis we have the time. As the you may notice that the relationship is not linear, it's a curve. That means that there is a change in the slope. The slope is maximum at the beginning, and then it gets smaller and smaller, so the reaction gets slower as we proceed. That kind of makes sense intuitively, because we have said that one of the factors that are important to determine the rate is the amount of collision, right? So if the more abundant is the reagent, the more likely that the collision could happen. However, things are a little bit more complicated than that. In this case, we can also tell that this is a reactant because the concentration is going down over time. So this is the instantaneous rate. Let's see now how to calculate the average reaction rate. So in this problem, we have a reaction between nitrogen gas and oxygen gas producing nitrogen monoxide. And we are asked to calculate the average reaction between 15 microseconds and 30 microseconds. So we have a table. So someone has been performing an experiment, and every 15 seconds they were measuring the concentration of the two reactants in blue. And since the concentration were always identical to each other, they just, to save space, they just wrote one column. And then they were also measuring the rate, they were measuring the concentration of the nitrogen monoxide, and those are the one here in magenta. So there is a difference, obviously. The reagent concentration are going down, and instead the products is going up, but they're also doing so at a different rate. And the reason they are doing so at a different rate is because there is a coefficient of 2 in front of the nitrogen monoxide. So every time I use up one nitrogen molecule, I'm making 2 molecules of nitrogen monoxide. So let's try to calculate the rate for one of the two reagents. As I said, they are going to do exactly the same thing. So we are going to take, so we are interested in the values between 15 and 30. So 30 is our final time and 15 is the initial time. So at the bottom we are going to put 30 minus 15. At the top we are going to put the difference between the concentration. So it's going to be final 3.6 minus initial 7.6. So the value we are getting is going to be negative because the concentration is going down, so the concentration is decreasing. Okay, so we have this minus sign here. If we repeat the calculation for the nitrogen oxide, that's a product, we have a different result. So as you can see, well, first of all, we get a positive, and that's because the concentration of the nitrogen monoxide is going up, but we actually get a different number. The number is twice as big. And this, as I said, is because of this coefficient 2, but that's very inconvenient. We want to have just one rate, regardless of the molecule that we decide to calculate the rate for, right? There should be only one rate for the reaction. So in order to fix this issue, we can modify the formula, we can modify the way we calculate the rate, right? So instead of doing that, we're going to make an adjustment, and we'll say, well, whenever we are calculating the rate at which reactant is disappearing, we're going to stick a minus in front of it, so that is going to become positive. So now we do have a positive number, and so we have solved one of the problem. And then if there is a coefficient in front of either a reagent or a product, so in this case we have a coefficient of 2 in front of nitrogen monoxide, we are going to divide the rate by that coefficient, right? So we're going to divide the rate by 2. And by using this little trick, we managed to get 2 identical rates. Okay, so in general, the formula is going to be the one highlighted here at the bottom. The rate is going to be, for the products, the change in concentration of the products divided the time, divided the coefficient. For the reagents, same thing, but you also need to use a minus sign. So let's see another example. Here, this is a reaction that you've been seeing in the video that I gave you to watch in the other, that was suggested in the other PowerPoint. This is also a reaction that you have actually performed in Gen 1 semester. It was the one with the marble chips, and you were dropping hydrochloric acid, and you need to be slow because otherwise you were going to have an overflow of hydrochloric acid on the bench, and you were producing CO2. And in that case, we used the reaction to determine experimentally the molecular mass of the CO2. But this reaction can also be used to determine the kinetics, because the marble chips are getting used up, so it's kind of relatively easy to measure how much the mass of the marble chips is going down during the reaction, because you can put the beaker on top of a scale. And you can also collect the CO2 that you're forming, so you can also measure that. Okay, so in this case we have a variety of coefficients. There is a coefficient of 2 in front of the hydrochloric acid, but there's a coefficient of 1 in front of calcium carbonate. That would be the material of the marble chips, right? Calcium carbonate is a very common constituent of minerals. So marble is calcium carbonate, the eggshell of the eggs, the eggshell is calcium carbonate, the shell of mollusks is also calcium carbonate, and so forth. So the rate of appearance of the CO2, according to this new way of, we just described, so it's a product, so we don't have to do anything with the sign. The coefficient is 1, so we don't have to do anything with that as well. So we just take the change in concentration divided the change in time. For the calcium carbonate, we are going to use a minus sign because it's a reagent that is disappearing. And this way we will have 2 rates that are identical. So this is a relative rate, it is expressing the rate at which CO2 is formed relatively to the rate at which the calcium carbonate is used up. If we want to compare calcium carbon rate of disappearance of calcium carbonate and with the rate of disappearance of hydrochloric acid, so they are both reactants, so for both we need to use the minus sign, but for the HCl we need also to divide by 2 because there is a coefficient of 2 in front of the hydrochloric acid. So this is another example with different reaction. In this case is the decomposition of nitrogen dioxide into oxygen and nitrogen monoxide. So it looks similar to the other one, but it's actually different. So in this table, you see that the concentration has been measured at 50 seconds interval. So initially you have no products, right? All you have is a reagent, and then obviously the reagent is going down while the 2 reactants are going up. And you can see immediately that the numbers are different. The concentration of the nitrogen monoxide is always twice as big as the concentration of the oxygen. And this is because there is a coefficient of 2 in front of the nitrogen monoxide. So every time I'm forming 1 molecule of oxygen, I'm forming 2 molecules of nitrogen monoxide. So I could graph these numbers, right, and make a graph out of it, and that's how it would look like. So we see some interesting things. So the blue curve, that's the nitrogen monoxide, is going up at a higher rate than the magenta curve, right? So at each point, the tangent would have more pronounced slope in the blue curve than it is on the magenta curve, the slope would be positive because the concentration are going up. For the green curve, the the slope would be negative because that's the disappearance of the reactant. So, in order to be able to write the relative rates at which reactants are used up or products are formed, we need to have the balance equation because we need the coefficient, right? So in this equation, you have the rate, the relative rate of all the species interested. So again, the pattern is a minus in front of the reagents, and then you need to divide each concentration by the coefficient in front of the species in the balanced equation. So in general, for a generic reaction where A, B, C, and D are the species and the small letter indicates the coefficient, okay, the rate could be summarized by this equation that is given in the cheat sheet in the cover of the exam. Not for the final, but for the partial exam, yes, it's given. So again, let's highlight the pattern. We add a minus sign if it's a reagent, and we divide basically by the coefficient. Oftentimes you're asked to calculate, so in the question they would pick two specific, not all four of them, but just two. For example, calculate the rate of A respect to B, or calculate the rate of C respect to B. So in this case, you want to write the equality only for the two species that you're asked the question about. So, for example, if they ask you to calculate the rate of A respect to the rate of C, there's no need to write this, so you can just ignore this part. There's no need to write that. The only equation that you need to write is that minus 1 divided A for the rate of disappearance is equal to this component, right? So you would write that. That's all you need. And then you want to solve for delta concentration of A divided delta T. So you want to bring the A on the other side of the equation. So you will get that. So that's how you do the math. So in general, when we were talking about the collision theory, right? So in order for the reaction to happen, you need to have a collision. And so it kind of makes sense that the concentration of the reactant is a critical factor. The higher is the concentration, the more reactants you have, the more likely that they have a collision. Therefore, you should expect that the higher is the concentration, the higher is the speed. That means that there is a very steep slope, as opposed to the situation where the concentration goes down and you should have a much smaller slope. This scenario, as I was saying, is more complicated because it depends basically on exactly what needs to happen for the reaction to take place. So what kind of a collision, how many molecules are involved in the collision. So we have different scenarios. And to describe the relationship between the concentration of the reagent and the rate, it's called the rate law. Right? So that would be the mathematical equation that would tell me what's going to be the rate given the concentration of the reactant. So this is how the rate law typically looks. So you have that the rate is proportional, and so according to a certain constant, proportionality constant K, is going to be proportional to the concentration of all the species that you see in the balance equation on the product side. So in principle, as a starting theory, we should assume that every species is important and is relevant. So I have A and B, I should assume that A and B are both important. How exactly, mathematically speaking, important they are, it depends on what we have as the exponent here. Okay, so m and n are the two exponents, and depending on the number we get, the role of the concentration of A and the concentration of B is going to be different. For example, if m, so the exponent for A is 1, the consequence is that if I have twice as much A, the rate is also going to be twice as big. But if A would be 2, if I double A, 2 elevated to the second power is 4, I make the rate 4 times faster. So the presence of an exponent that is higher than 1 makes the effect of changing the concentration of that specific species more critical. So what kind of value do m and n typically have? They are typically whole numbers, positive, so like 1, 2, 3, including 0. So let's see what does it mean if one of these numbers is 0. Any base elevated to the 0 is equal to 1. So that would mean that if, let's say, n would be 0, b elevated to the 0 would be 1. That means that I could pretty much cross out b. That would mean that no matter what I do with b, I can make it much bigger, I can make it much smaller, the rate is not going to be affected, right? That may seem like a counterintuitive thing. How could it be that one species that's a reagent doesn't matter to the rate? And we will see how that could happen. So in general, K is the rate constant, and it has units that can be different depending on the circumstances. The exponent m and n are called order. So we would say that the reaction is of m order respect to A, and it's of n order respect to B. And the overall total order of the reaction would be m plus n. So by summing up those two exponents, you get the total. Let's see some example. Let's start with 0 order. So if the reaction is of 0 order respect to A, it means that the exponent that we have to write for the concentration of A is 0. As a consequence, because any base elevated to the 0 is equal to 1, we can actually write the rate law as such. It may seem counterintuitive that the rate is totally independent from the concentration, right? Because if you look at the graph, you see a straight line with a negative slope. So basically what it means is that no matter if the concentration is high or low, so no matter if we are here or here, the slope is always going to be the same. The rate is always going to be the same. And since we have talked about the collision theory and how in order for the reaction to happen there has to be a collision, it seems kind of counterintuitive how that could be possible, right? Because if you have low concentration, then the collision should be quite harder to happen, quite more rare. So a typical situation where you can find a 0 order reactions that are pretty rare, but they tend to occur especially in biological situations, like for example the reaction that are catalyzed by enzymes. So the reaction in our body tend to happen thanks to the role of enzymes that are larger protein. And this protein have an active site that is almost similar to a lock, where the substrate, that would be whatever molecule is going to undergo the reaction, is the key. So the key needs to fit perfectly in the active site for the reaction to happen. So this allows the reaction to happen faster in our organism, but also in a very specific way. So basically we could write an equation, a balanced equation for this reaction, and you would see that the enzyme doesn't appear. So it's not reactant because it doesn't get used up, and it's not a product because it doesn't get produced. I start with one molecule of enzyme, and by the end of the reaction I still have that very same molecule of enzyme. So it doesn't belong on either side of the equation. And so if you would just look at the balance equation, you wouldn't even know that that's happening through an enzyme. But the thing is, the actual rate, because normally biological, inside a cell or inside an organism, you tend to have a large excess of the substrate. You have a lot of substrate, and you have only a limited amount of molecule of enzyme. For example, when you're transporting oxygen through hemoglobin in the red cells of the blood, the bottleneck is how many molecules of hemoglobin you have. So even once you have saturated that, once you have every single molecule of hemoglobin is bonded to an oxygen, you could increase as much as you want the amount of oxygen in the air that you're breathing, but that wouldn't increase at all the amount of oxygen that gets to the peripheral tissue, because that depends on how many molecules of hemoglobin you have. So, and this is why, in this situation, the concentration of the substrate becomes irrelevant. So we are talking about pseudo-zero order in this case. This is the graph you would obtain if you would have a reaction that is first order. So first order means that there is a coefficient of that there is an exponent of 1 in the concentration in the rate law, and that it's equivalent to say that there is direct proportionality between rate and concentration, and the constant of proportionality is the kinetic constant. So this means that if I have a lot of reactant, and like here in this part of the graph, I would have quite a steep slope, and so a fast reaction. When I have very few molecules of reactant, the slope becomes smaller and the reaction becomes slower. Now, typically we don't get really excited to have to graph a curve. Like, it's much easier to draw a straight line because all you need is a ruler. So in general, we're always looking for little tricks, mathematical manipulation that allows us to transform a curve graph into a straight line. And in this case, the trick is to plot on the y-axis the logarithm of the concentration instead of the concentration as it is. So you see on the x-axis we have time in both, so we don't do anything with that, we don't change it at all. But by changing the y variable from concentration to logarithm of the concentration, we get a straight line. Typically you would use the natural logarithm. Actually, if you would use the decimal logarithm, of course the number is going to be different, right? So the natural logarithm of a certain concentration of A is going to be a certain result. If you calculate the decimal logarithm, you're going to have a different number. But in terms of graph appearance, it's still going to be a straight line, because the two different logarithms are proportional to each other. You can convert from one to another just by using a multiplication. So I'm just saying, because if you see a question in a test and the picture has decimal logarithm by any chance instead of natural logarithm, is still the fact that it's a straight line is still telling you is first order. That's typically the kind of question you get. Relate the shape of the graph to the order. Rarely you have to do math with this type of graphs. It's more about, since if when I put it on a logarithmic scale, it becomes a straight line, what can you infer about the order? And you should answer, I can infer that it's first order. This is the second order, so it's still a curve, but you can tell probably that it's steeper than it was before. So by decreasing the concentration, we get a much more dramatic change in the rate. It's hard though to tell just by looking at the shape of the curve if it's first or second order. What really gives it away is what transformation would make it a straight line. As we've seen for first order, the transformation would be plotting the logarithm. For second order, the transformation is plotting the reciprocal. Because you're plotting the reciprocal, the slope now becomes positive. Okay. So you can tell from here that if I would double the concentration, so if the concentration goes from A to 2A, the 2 would be elevated to the second power, would become a 4, so the rate would be increased of 4 times. So the effect of changing the concentration over the rate is much more dramatic. Now, typically, the most common order is 0, 1, and 2. Fractional order do exist. Negative orders do exist. They are rare, and you don't have really to worry about it. I'm happy if you understand the difference between 0, first, and second. We're going to keep it simple. So, in general, right, when you have a balanced equation, this is your balanced equation, and this is your rate law. Now, you might have noticed at this point that I took great care of using different symbols for the exponent that I used for the coefficient in the balanced equation, right? The coefficient in the balanced equation are A and B. The exponent here are M and N. So M is the order of the reaction order respect to A, N is the reaction order respect to B, and the sum of the two is going to be the overall reaction order. But those numbers typically are not equal to A and B. Okay, so this is very important because this is the most common mistake you will do. Just by looking at the balance equation, there's no way you can write the rate law. The only way, because you don't know exactly what's happening in that reaction. The rate law depends on the mechanism, the type of collision that you need to happen. And just by looking at this, you cannot really tell, just by looking at the balance equation. So the only way to determine the rate law is either you perform an experiment in the lab or someone else perform an experiment and gives you the numbers in a problem. There may be sometimes situation where M is equal to A, but that's the exception, not the rule. This is the second warning, right? Rate laws must be determined experimentally. And the method is called the method of instantaneous reaction rate at time 0. So it's called the method of the initial rates. And this is what you will do in the lab. That's going to be virtual lab instead of an actual lab, but that's what it is, right? So in order to manage to determine the rate law, we need to perform an experiment, and these experiments are based on the method of the initial reaction rates. So we're going to measure the reaction rates at the very beginning of the reaction, because even if we have simplified things, assuming that reaction happen in only one direction, so that they are irreversible, actually what happens most of the time is that as the products accumulates, they may decide to react back and retransform into the reagent. And so that would, of course, complicate extremely the whole determination. So, but if we perform the experiment, the measurement, the very beginning of the reaction, when there is still a lot of reactant and the concentration of the product is very small, we can avoid the problem. So in this way, we can determine the rate law by determining the rate at different concentration of A and B. So we can manipulate A, change it, and see what happens, and then change B and see what happens. The problem is we have a lot of unknown here. We don't know N, we don't know M, and we don't know K. So there are 3 things that are unknown. So this can complicate a little bit the experimental design. The K has units, and the units depends on the value of M and N. So think about solving for K. K would be equal to the rate divided the concentration of reagent A elevated to the M power and the concentration of reactant B elevated to the N power. And the rate is molarity per second. And A and B are also molarity, but depending on what you have as an exponent, the simplification is going to give you different results. So the unit of K do depend on the order of the overall order of reaction. That means that sometimes you can get questions where you're given the value of k with the units, and they may expect you to figure out what order the reaction is based on the units. I will not do that. So in order to use the method of the initial rates, you need to perform a set of experiments. Okay, so several experiments in each of these experiments you're going to change the concentration of either A or B, and then you're going to compare them 2 by 2. It sounds more complicated said this way, and it's going to make more sense if we look at an example. So this is an example of an experimental design. We perform 5 separate experiments. Sometimes we are changing the concentration of A. So you see there are 3 experiments in which is 0.50. And then in experiment 2 is increased a bit, and in experiment 3 is double. And then we have several experiments in which B is held constant, and then in experiment 4 you have increased B twice, so it's as big, and then here is multiplied by 3. So and for each of these experiments you're going to measure the rate as in this case is molarity per hour. So we need to observe carefully the experimental design, and we want to pick 2 experiments in which only one of the initial concentration is changed. If we change 2 things at a time, the picture becomes too complicated to be able to extract any useful information. So let's get 1 and 2, right? If we compare 1 and 2, we see that B is held constant. So really the only thing that's changing between experiment 1 and experiment 2 is the concentration of A. So whatever effect we see, we can be sure that it depends only on A. Now the other thing that's critical is the temperature, right? As we said, a change in temperature will change K. So we don't want K to change, we want K to be constant. So we need to make sure that the temperature during the experiment is held constant. So let's focus on the first 2 experiments. What I'm trying to determine is the rate for this reaction. So I will have to figure out what's the value of K, what's the value of N, and what's the value of M. Now for the time being, I'm just trying to take one step at a time and focus on M. And that's the reason why I took 2 experiments in which the concentration of B was constant. Because this way I know that whatever effect I'm seeing on the rate is going to be ascribed to A. A is going to be for sure the only responsible variable for that effect, right? So I'm starting to write the rate law for my first experiment. And if I substitute the value that I have, right, I know what the rate is 0.50 times 10 to the minus 2 molarity per hour. I know that the concentration of A is 0.50, and I know that the concentration of B is 0.20. My problem is I have a lot of unknown. I don't know what N is, I don't know what M is, and I don't know what K is. So I have 3 unknown, and that's not going to work with one equation. So what do you do in math where you have multiple unknowns? You need to increase the number of the equation. You need to build a system. So in this case, we can write the same rate law for experiment 2 and plug the numbers. So we see that there are a couple of things that are the same. K is the same, M is the same, and N is the same. As long as we don't change the temperature, K is not going to change and is a constant. So if we divide the first equation by the second, we can do a number of simplification. We can get rid of K because it's the same value, and we can get rid of 0.20 to the N. We don't know what N is, but the same base elevated to the same exponent is going to be the very same number. So if I don't know what that number is, I'm pretty sure it's going to be identical, and I can simplify. So in this particular situation, the two rates happen to be the same. That means that the ratio here is 1. So the equation becomes 1 equal 0.50 divided 0.75 elevated to the m. So because now I'm much more confident because I have only one unknown, and it's an exponent, so I need to use logarithm to solve this equation. So the logarithm of 1, that is 0, is going to be equal to m times the logarithm of 0.50 divided 0.75. Now I'm not even bothering plugging that in the calculator because knowing that the logarithm of 1 is 0, the only way that equivalence may work if its m is going to be equal to 0. So I can just save time and write m equal to 0. So I figured out that the reaction is 0 order respect to A. They kind of make a lot of sense if you think about it, because changing the initial concentration of A from 0.50 to 0.75, so with an increase of 50%, did not do a thing to the rate. The rate was totally unaffected. So that means that the concentration of A is irrelevant in terms of rate, and that means that the order respect to A is 0. Now let's see a different set of experiments, 1 and 4. Why do I pick 1 and 4? Because in 1 and 4 the concentration of A is the same. So this time the only thing that's changing is the concentration of B. Whatever is happening to the initial rate, and I can tell that the initial rate is doubling, I'm pretty sure is happening because of B. So I follow the same procedure. I write the rate for the first experiment, experiment number 1. I plug the numbers, and then I rewrite the rate law for experiment number 4. And I plug the numbers. And now I divide the first equation for the second one. I have again things that are identical. K can be simplified. I'm not changing the temperature, so K is not changing. 0.50 to the m, whatever m is going to be. Now I know that's 0, but let's imagine we started from here. It's going to be the same, so I can simplify that. So my equation becomes 0.50 divided 1 is 0.50 is equal to 0.50 elevated to the n. So sure, I should use the logarithm, but it's pretty obvious that n is going to be equal to 1. So I figure out that the reaction is first order respect to B. So now I know that m is equal to 0 and n is equal to 1, and therefore the only unknown is K. I can calculate K. I have my rate law, and I can just pick one random experiment. The results should be the same for each of the 5 experiments. Obviously you have to do it only once, so let's be original and use some fantasy, and let's just pick one. So the rate is 0.50 times 10 to the minus 2 is going to be equal to K times the concentration of B, because the concentration of A is irrelevant, being order 0. So that allows us to calculate A. Now, most of the time, and this is especially correspond to the type of problems you get in the final, there's a way to solve the problems without using any algebra. And this happens whenever the concentration are manipulated according to nice, simple ratios. So you see, for example, that between 1 and 4, right, I have the same concentration of A, the concentration of B doubles. So doubles is a simple number, it's times 2. What happened to the rate? The rate doubles. Okay, so if the manipulation of B reflects into the same change in rate, it means that there is a direct proportionality. When one doubles, the other one doubles. So that tells me it's order 1. If we look at a situation where B is constant, for example, 1 and 3, B is the same, but A is doubling. So I can tell that by doubling A while keeping B constant, nothing happens to the rate. So that should give me the answer that the order respect to A is 0. So this is the rule of thumb. When you have 0 order, doubling the reactant have no effect on the rate. Cutting in half the reactant has no effect on the rate. Be careful with these graphs here. You see that the on the y-axis, so far we've been seeing concentration, and so we were seeing curves or straight lines with negative slopes. But now we are plotting something completely different. We are plotting the rate on the y-axis. So if the rate is constant, you get a nice horizontal line. That's 0 order. If said less like constant velocity, right? This would be constant. This would be an accelerated with a constant acceleration, and here instead you have the second order. So but basically, if the change in concentration corresponds to simple ratio like doubling or cutting in half or multiplying by 3 or dividing by 3, for 0 order nothing happens to the rate. For first order, whatever you're doing to the concentration is exactly mirrored by the change in the rate. For second order, you have a second power. So for example, when you're doubling the rate, when you're doubling the concentration, the rate will become 4 times bigger, because 4 is equal to 2 to the second power. Okay, so let's check your comprehension with this question. The reaction is second order respect to C. What happens when I triple the concentration of C? The concentration of C is 3 times larger. What happened to the rate? Does it stay the same? Does it become 2 times larger? Does it become 3 times larger? Does it become 9 times larger? What do you think? Okay, so time to see what happens. What happens is that the rate, if the first concentration was, let's say, 1, and then it becomes 3, is 3 to the second power is 9. So the new rate is going to be 9 times the rate that you had before. So finally, the really important point is that the rate loss needs to be determined experimentally. Normally, you cannot look at the coefficient in the balance equation to figure out what M and N are.